Welcome back. We are now starting logarithmic functions. Now, the definition of a logarithmic, and I want you to put the word function in quotes. The trigonometric functions, logarithmic functions, mean that you have a notation like f of x. There's going to be an argument at the end, sine of theta, logarithm of some number. It's denoted by log where there's a base b, and it's defined where if you have log of the base written there as a subscript below near the bottom of the g of some argument x equals y, that can be written in exponential form. Now I call this the swirly-do definition. If we circle the base of the logarithm, the b, the base of that logarithm is the same thing as the base of an exponent. So if you took b to the power of y, it should equal your argument x. In other words, we can rewrite that logarithm as base b to the exponent of y equals x. Now, in logarithms, we do have some restrictions. Our base has to be a positive number. If it's negative, then when you take it to a different exponent, it's just going to oscillate between a negative and a positive number. Also, our base cannot equal 1. Otherwise, no matter what the exponent is just going to give us 1. So might as well just write the number 1. And since our base has to be positive, that means that argument of x also has to be positive. So we've summed that up in the box below, logarithmic form and the exponential form. So when we're reading a logarithm, such as the one given in that first bullet point, that would be read log base b of x equals y. So x is our argument, but y is what a logarithm equals. So log base b of x equals or is the exponent. That is a huge concept with logarithms right here. Logarithms represent exponents. So that log is the exponent that you have to raise b to in order to equal x. And we're going to do some examples here in a minute. So since exponential and logarithmic functions are inverses of one another, that means that their domain and ranges are switched. So the logarithmic function has a domain from 0 to infinity, 0 not included, and a range from negative infinity to infinity. Now there's two specific types of logarithms. The first one is called the common logarithm or common log, and it has a base of 10 since we work in a base 10 number system. Tens, hundreds, thousands, 10,000s, and it's denoted by log with an x. Notice there's no base seen. We would just read that common log of x. The next one we call the natural log, and the natural logarithm has a base of e, Euler's constant, and it's denoted by ln of our argument, and we would just say take the natural log of x. So we could write it with a logarithm with a base e, but this is a shorthand. Now, I want to show you guys something on your calculators. So if you look on the left-hand side here of your calculators, you see the log and you see the ln, but look at the second function that's noted above each of those buttons. On top of the log or the common log button is 10 to the x. So that's even kind of a nice little cheat sheet on your calculator reminding you that if you don't see a base, that common log has a base of 10. Likewise, the natural log, the ln button here, has a second function, e to the x, to remind us the base of the natural log is e. Well, we're not going to be using our calculators just yet. We want to get used to what a logarithm represents first. So in this first example, we want to rewrite the exponential equation 2 cubed equals 8 as an equivalent logarithmic equation. So remember, if we start with log, the base of our logarithm is also the base of the exponent. So the base of our exponent is 2, so we're going to have log base 2. And remember, the logarithm represents the exponent. So I usually write the equal sign first. So 2 cubed equals our argument 8. So we have log base 2 of 8 equals 3. Again, you can kind of see where the swirly-do comes from. So just always start with your base. So in part B, we want to rewrite the logarithmic equation log base 3 of 1/9 equals a -2. Base 3 is going to be the base of our exponent. So we have 3 to the power of -2 equals our argument, which is 1/9. And that's a true statement. Remember, negative exponents means reciprocal. And if we square 3, we get 9. So let's do several examples. And we want to evaluate each expression if possible. So there's a hint that some of these may not be possible. So log base 5 of 125. This is asking us 5 to what exponent would give us 125? Well, that would be 3, since 5 cubed equals 125. We have the logarithm base 4 equals 1 over 256. Sometimes it's helpful to rewrite that argument in terms of your base. For example, this log of base 4 is equivalent to 1 over 4 to the 4th power. If we didn't want to write it as a reciprocal, we can use our negative exponents, 4 to the -4. So this is asking us 4 to what exponent would give us 4 to the -4. So 4 to what exponent would give us 4 to the -4. When you rewrite it like that, it feels almost like Sesame Street logic, you know, this side must look like the other. So it has to be 4 to the power of -4 in order for it to equal 4 to the -4. Part C, notice we do not have a base that is seen. That means if it has the log that we are using a common log. The common log of 100 is asking us 10 to what exponent gives us 100? Well, that would be 2, since 10 squared equals 100. So that base there is an understood 10. Part D, here we have a natural log of 1. This is asking us e to what exponent equals 1. Because remember that base, even though we don't see it, is an understood e. So the natural logarithm has a base of e. So e to what exponent equals 1? Well, there's only one exponent that no matter what base we have, to this exponent, it always equals 1. And that is 0. So anytime you have a logarithm, regardless of the base, if it is a logarithm of 1, it will always equal 0. Here we have another common log. So this one is asking us base of 10 to what exponent would give us a -10. Is there one? Even if we took it to a negative exponent, that wouldn't change it to a negative number. It would just take the reciprocal. Like 10 to the -1 is 1/10. Even 10 to the 0 power is a +1. So remember at the beginning, we said that that argument, that x value, has to be positive. So this one does not exist. And the reason is since -10 is not in the domain. What about the natural log of 0? That's asking us for the exponent that if we took e to that exponent, it would give us 0. Well, even e to the 0 power gives us 1. So whether it's a negative exponent or a positive exponent, this one also does not exist because remember our argument has to be greater than 0, not greater than or equal to. Because remember our domain was greater than 0, not greater than or equal to. Now let's take a look at G. Okay, so this is going to take a little bit of thinking. We have 10 as a base, but it's a base of an exponent. The logarithm is in the exponent position. So before we simplify this, let's take a look at what log of 7 is saying. So that's an understood base 10. What this equals is 10 to that exponent should give us 7, whatever that exponent is. Well, we don't know what that is. So what we can do is define it as, let's say, an n. Log base 10 of 7, or the common log of 7, equals some number n. That's the exponent. Well, guess what? We are taking 10 to that exponent. We can substitute it in for that exponent minus 1. Well, remember what that logarithm means. 10 to the power of n equals 7. So we can use substitution. So that equals 7 minus 1, which gives us 6. So if you have a base of 10, let's say, or any base, taken to a logarithm of the same base, it's going to equal your argument. Matter of fact, let's write that out to the side. We'll get into these properties a lot more later, but it's saying if you have a number, let's call it p, and it's taken to the logarithm base p of some argument, remember that logarithm represents the exponent that would give you x. Well, p is being taken now to that exponent, so it would equal just x. This is the same issue. We have a natural log, therefore we have an understood base e. So e to what exponent would give us e to the negative 3.5? Negative 3.5, which gives us a 1.5. So again, just a little scrap work down here. That means e to what exponent would give us e to the negative 3.5. Base of the argument equals the base of the logarithm. So these two here should be the same. So that's why it just equals negative 3.5. So we get 1.5. So you're going to practice some of these in your homework if you can get them in terms of the base, and if you need to rewrite the base for like the common log or the natural log, write in that 10 or the e, go for it. Just notice there in H, some people think that E is already in the base, but it is not. If you see that LN, that base is never written. So if it helps you to write it in at first just to see it, to know that those are two different E's there. Remember in the last section, we talked about how logs represent exponents. So when we're talking about these properties, they're going to follow along some of the exponent rules that we already know. Some of these properties we've already alluded to in the previous section with our examples. Number one here, log of any arbitrary base b of an argument of 1 will always be 0. That's because anything to the 0 power is 1. If the base and the argument are the same, that will equal 1. That is because any number to the power of 1 is itself. The inverse property focuses on the fact that logarithms represent exponents. B to what power will give us m? Well, b is being taken to that power, therefore it gives us m. So these two bases must be the same. Likewise, if that base is within the argument, it equals r. There's a one-to-one property that states if you have two logarithms equal to each other and the bases are the same, then the arguments must also be equal to each other. That helps when we're solving some logarithm equations. Then we have a product rule. This product rule is based on the fact that if we have, let's say, a number x to the n times x to the m, if we multiply like bases, we end up adding their exponents. The same is true of the logarithm. If the arguments are being multiplied, we can split them up as log base b of the first argument plus log base b of the second argument. Likewise, with the quotient rule, if we had x to the power of n divided by x to the power of m like bases, then we would keep that base and subtract the exponents. So when we're dealing with logarithms, we can split up an argument that's being divided using subtraction. So that would give us log base b of m minus log base b of n. Also with power rules, with exponents, if we had x to the n taken to the power of m, in other words, an exponent to an exponent, we multiply those exponents. X to the n minus m. Logarithms follow the same format. If you have log base b of an argument m to the r, we can take that exponent and move it to the front and multiply that r times that logarithm that's representing an exponent of an argument m. Put an asterisk by this one or maybe highlight it. We're going to use this one a lot when solving exponential functions. This guy Just like the Pythagorean was the granddaddy in trig, this power rule here is kind of a granddaddy when we're solving exponential functions. It's the only way to get an exponent out of the exponent position. Last but not least, we have a change of base formula, log base b of m. And I realize some of your calculators now actually do different bases other than just common log and natural log. But the change of base formula you can do on any scientific calculator. It is the common log of your argument divided by the common log of your base. We can also use natural logarithm. It gives us the same ratio. So let's do a couple of examples. They first want us to expand each of these logarithmic expressions into a sum or difference of logarithms. What this means is we may have more than one logarithm, but no exponents or multiplication or anything like that. Don't forget your bases, don't drop. So you may notice that in our argument, we have multiplication, 9 times x squared times y to the fourth. When we are multiplying like bases, we add exponents. So we can split up this logarithm as log base 3 of 9 plus log base 3 of x squared plus log base 3 of y to the fourth. And we really don't want those exponents there either. So we're going to use that granddaddy that I told you about, and we're going to take all those exponents and move them to the front of their individual logarithm. So log base 3 of 9 plus 2 log base 3 of x plus 4 log base 3 of y. Now it looks like we're done because everything is simplified, except we can go further with that first logarithm. Notice you have a base 3 and an argument of 9. There is an exponent. 3 squared gives us 9. So this entire logarithm can be replaced with the number 2. So we get 2 plus 2 log base 3 of x plus 4 log base 3 of y. In our next logarithm, we have a couple of operations. We have multiplication on the top, but we also have division. So let's work with that larger operation of division first. Remember, when we're dividing like bases, we subtract exponents. So when we're dividing the argument and the logarithm, we're going to split it up with subtraction. So the log y is pretty much set, but there's more that we can do with the log 1000 square root of x. They're being multiplied. So we can rewrite this multiplication as log of 1000 plus log square root of x minus log of y. Now, even though that square root of x looks like it's simplified, we can write it with a fraction exponent. So log of 1000 plus log of x to the 1/2 minus log of y. So if you've forgotten some of those rules, if you have the nth root of x to the r, it can be written as x to the r, but divide that exponent by the index n. So that's why this is an understood 1. Understood square root, that's where the 1/2 came from, just a little reminder. So we can move that 1/2 to the front of that particular logarithm. And again, it looks like we're done, except it's a common log. Common log is a base 10, which means that first logarithm can be simplified into just an integer. We have the log base 10, 10 cubed would give us 1000. So that logarithm would be the exponent 3. So we get 3 plus 1/2 log x minus log y. That would be our final answer. Now in these next 2 or 3, they want us to combine these logarithms, condense them using the properties, because the properties go in both ways. This is very important when you're trying to solve a logarithm equation. You want to get it down to one logarithm. So this is a good practice. Focusing on the first one, we have subtraction. And remember, when do we subtract exponents? When we're dividing. So we change this to a single natural log with the argument of the first guy, x plus 3, divided by the second guy, which is x. Notice we did not distribute natural log into that first binomial. Natural log is not a number. We cannot distribute or divide by it. It is a function. So you can only work with it as such. For part B, we have a couple of things going on. Notice in both logarithms, there is a coefficient in the front. We can actually move that coefficient back into an exponent position for both. So the first logarithm would be log base 3 of x plus 2 to the power of 1/2 plus log base 3 of x squared. Remember that 1/2 does mean square root. So we can write that as log base 3 of the square root of x plus 2 plus log base 3 of x squared. Logarithms represent exponents. When do we add exponents? When we multiply like bases. So we're going to multiply our arguments. So we get log base 3. I'm going to move the x squared to the front of the square root, just so it doesn't look like that x squared might be underneath the square root. And we want to put parentheses or brackets so we know that both of those are part of the argument. All right, in part C, again, we have a couple of things going on. Let's move this coefficient of 2 first. So common log of 9 does not change, plus the common log of x cubed. We're going to move that 2 and make that an x cubed squared, minus the common log of x minus 4. We can simplify that x cubed being squared. So we get common log of 9 plus the common log of x to the 6th. Remember, power to a power, we multiply, minus the common log of x minus 4. Remember, we cannot distribute a logarithm, so that x minus 4 is stuck. It doesn't change to multiplication or get spread out. Now let's focus on the addition and subtraction left to right so we can combine our logarithms. The first one is addition. Logarithms represent exponents. When do we add exponents? When we multiply like bases. So we're going to take this common log and we're going to multiply the 9 times the x to the 6th. And we still have the minus log of x minus 4 at the end. So now we have two logarithms that are being subtracted. Logarithms represent exponents. When are exponents subtracted? When we divide. So we can rewrite this as logarithm of 9x to the 6th divided by x minus 4. And again, put parentheses around your argument so we know that that entire thing is our argument of the logarithm. In example 3, they want us to use the change of base formula to estimate, and there is a huge hint there, estimate log base 2 of 9, and then round your answer to 3 decimal places. The word estimate and round your answer is a hint we're going to be using our calculator, because there's no exponent of 2, a nice number that we know of anyway, that would give us 9. So in our calculators, we can put log of 9 divided by log of 2, and that would give us approximately 3.169925001. But some of us have been getting our homework problems wrong, not because we're doing the work wrong, but because we're not rounding our answers correctly. So when it says to round to 3 decimal places, 1, 2, 3, we still have to look at that next number and round up. Granted, that's going to give us not, if we look at it like hundreds, 169, it's going to round up to 170 or 0.170. So we get 3.170 as our answer. Be careful about putting in log 9, rounding it, and then log 2 and rounding it, because it may not give you the answer that you need to 3 decimal places. You only want to hit enter on your calculator once. So we're going to graph each of these logarithmic functions by plotting points. So remember, if we write that as log base 2 of x equals y, using our swirly-do definition, That's the same thing as saying 2 to the exponent of y will equal x. If we're to do an xy table and plot points, it may be more helpful to actually put in values of y first instead of x. So we can go from -2 all the way to 2 with our integers and plug it in. So 2 to the -2 would give us an x value of 1/4. 2 to the -1 gives us an x value of 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 squared gives us 4. So let's plot each of those points. When x is a positive 1/4, y is a -2. When x is a 1/2, y is a -1. X is 1, y is 0. When x is 2, y is 1. And when x is 4, y is 2. So we have a nice increasing function. Notice there, no matter how close to -infinity we get for y, we're still going to get a positive reciprocal. So our graph is not crossing that y-axis. Now let's look at the function g of x equals log base 1/2 of x. If we rewrite that, log base 1/2 of x equals y. And again, think of it in terms as our swirly-do definition. That would give us 1/2 to the power of y equals x. So if we plug into an xy table to come up with points, again, we'll probably want to plug in for our exponent or y value first. So we'll use y values of -2, -1, 0, 1, and 2. 1/2 to the -2, you take the reciprocal and square it, we would get a positive 4. 1/2 to the -1 gives us a positive 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2, and 1/2 squared is 1/4. Let's plot these points. When x is 4, y is -2. When x is 2, y is -1. X is 1, y is 0. When x is 1/2, y is 1. When x is 1/4, y is 2. So we have a decreasing function. And again, notice how close to -infinity our y becomes. Our x just approaches infinity, but it never becomes 0 or negative. It never crosses the y-axis. So let's take a look at some of the characteristics of the graphs of a parent logarithmic function. In other words, f of x equals log of some arbitrary base b of x. Remember, b cannot be negative or 0. And x has to be larger than 0, in other words, positive, and b cannot equal 1. Is it a function? Yes, it passes the vertical line test. One-to-one function? Yes, it also passes a horizontal line test. So that means we can find an inverse. Horizontal asymptote, there doesn't seem to be a value that the y is approaching when the x gets large, either positively or negatively. There are no horizontal asymptotes. However, there are vertical asymptotes. Notice we're not shifting left and right. It is not crossing the y-axis. So that's a vertical asymptote of x equals 0. The domain, notice it's only starting right after 0. So our domain goes from 0 to infinity to the right. Our range, however, covers everything top to bottom. So we go from -infinity to infinity. Our x-intercept is at 1, 0, whether it's increasing or decreasing. Since it's not crossing the y-axis, then there is no y-intercept. It is increasing in that first graph from 0 to infinity, but notice in that first graph, our base was greater than 1. In the second graph, it's decreasing, still from 0 to infinity, but in that one, our base was between 0 and 1. In example 2, they've asked us to find the domain of this logarithmic function below and express it in interval notation. Remember, when we have any log base b of its argument equals y, we know the base has to be positive and it can't be 1, which means our argument also has to be positive. Well, in this case, our argument is not just x, our argument is a linear expression. So that still holds. 7 minus 2x has to be positive because 5 to any exponent will give us a positive number. So we can solve for this inequality. We can subtract 7 from both sides. And remember, when we divide both sides by a negative, we have to switch our inequality sign. So we have an x less than 3.5. So if we write that in interval notation, x is everybody to the left of 3.5. So that is negative infinity all the way to 3.5, 3.5 not included. If you're still struggling with interval notation, draw the number line, put in your 3.5. We know it's not included. X is everybody to the left, which means it's going towards negative infinity. And remember, our interval notation is always written from left to right, smallest to largest. So that's why it's negative infinity first, 3.5 next. So that guy is our domain. Now we have transformations, and again, transformations haven't changed. They just look different because they're now in a logarithm. That a that's being multiplied by the parent function, the logarithm in the front, is still a vertical stretch. So it is a stretch if that absolute value of a is greater than 1. It's a compression if that absolute value of a is between 0 and 1. And again, we're focusing on the absolute value because if it's negative, if a is less than 0, then that means we're multiplying the y values by a negative, and when y values change from positive to negative, that means it's reflected about the x-axis. On the other hand, if it's our x value that's being multiplied by a negative, our argument on the inside, our x values are changing from positive to negative, that means it's reflected about the y-axis. Our horizontal shifts has to deal with that change in c. Notice where we have that minus c there with x. So it's going to move either left or right, but it's going to be in the opposite direction of the sign of our c. Our vertical shifts of that plus d at the end is going to move in the same direction as the sign of d. So notice, none of those have changed from the exponentials or even the trig functions that we worked with. So let's look at example 3. You want to use transformations to graph this function, negative log base 2 of x minus 3 quantity and plus 1. You want to state the domain, the range, and the asymptote. Our parent function here would be y equals log base 2 of x. And we've actually graphed this function where we had x is 1, y is 0. If x is 2, y is 1. Then x was 4, y was 2. 1/2 was negative 1, 1/4 negative 2. And so here's our original function, log base 2 of x. So now let's take a look at the transformations that are occurring. And remember, we have to do the reflections and the stretches first. Well, we notice at the beginning our a is negative 1, which just means it's reflected about the x-axis. In other words, we're changing all the signs of our y's. Well, we can do that first. Let's do that in green. So if we take the point 4, 2, we're going to shift it down to 4, negative 2. The point 2, 1 will go down to 2, negative 1. 1, 0 will stay at 1, 0. 1/2 negative 1 will move up to a positive 1, and the point at negative 2 will move up to a positive 2. So that is just the reflection. In other words, the negative log base 2 of x. We'll even write that underneath here. Here was step 1, negative log base 2 of x. Now we need to look at our shifts. So in step 2, since we have an x minus 3 and then a plus 1, that means we're going to shift right 3 and also shift up 1. So for everything, every point that we have, everything gets shifts to the right, 3. That includes our vertical asymptote. Since our original vertical asymptote is at x equals 0, here, we're going to move it to the right 3 places. Here, x equals 3. And shifting it up or down 1 isn't going to make a difference because it's a vertical line. Now we take all of the points that's there in green, the one that's decreasing, it's been reflected, And we're going to take all those points, shift them right 3 and up 1. So starting with the point 4, -2, we're going to go right 3, 1, 2, 3, and up 1. Point 2, -1, we're going to go right 3, up 1. Point 1, 0, right 3, up 1. Then the point 1/2, 1, we're going to go right 3 and up 1. And the point 1, 4, 2 to the right 3 and up 1. So this last graph in black is our f of x functions with all transformations. Now they wanted us to state the domain, the range, and the asymptote of this new function. Now we can look at the picture to find the domain, but we can also look at just the argument. The +1 doesn't come into effect. Our argument was x minus 3. That has to be greater than 0. Add 3 to both sides. X has to be larger than 3, which is true. Our entire graph is to the right of that vertical asymptote of x equals 3. Our range does not change because it's going to continue to increase towards the left and decrease towards the right. So it goes from -infinity to infinity, and we have a vertical asymptote at x equals 3. All right, folks, that is it for section 4.4. If you have any questions, please don't hesitate to contact me. You know where to find me. Thanks. See you soon.